Welcome, gentle traveler, to the hidden highways of our planet. The vast, invisible rivers that flow beneath the waves, carrying warmth, life, and memory across the endless blue. Tonight, we embark on a journey into the secret world of ocean currents, those silent streams that shape our climate, guide marine life, and connect every shore to every other in an endless, graceful dance. Close your eyes and imagine the ocean not as a still, uniform body of water, but as a living network of flowing rivers, some warm, some cold, some swift, some slow, all weaving together in patterns as ancient as the earth itself. These are the currents that have carried explorers across unknown seas, brought nutrients to distant shores, and whispered the secrets of one hemisphere to another. In the beginning, there was stillness, but the earth, in its infinite wisdom, could not remain motionless for long. The sun, that great furnace in the sky, began to warm the waters unevenly, heating the tropics with its direct rays while leaving the poles in cooler shadow. This simple difference in temperature became the first breath of movement in the ocean's vast body. Picture the equatorial waters, bathed in golden sunlight, growing warm and light, eager to rise and spread. Meanwhile, at the poles, the water grows dense and heavy with cold, sinking into the depths like a slow, patient sigh. This is the beginning of what oceanographers call thermohaline circulation, the grand conveyor belt of the sea, driven by differences in temperature and salinity. But temperature alone does not create the intricate patterns we see today. The Earth spins on its axis, and this rotation, the Coriolis effect, gently deflects moving water, creating the spiraling gyres that dominate each ocean basin. In the northern hemisphere, currents curve to the right. In the southern hemisphere, to the left. It is as if the planet itself is conducting a vast, slow symphony, guiding each current to its proper place in the grand design. Imagine, if you will, the ocean as a great cathedral of water, with currents flowing at different levels like the voices in a choir. At the surface, driven by wind and sun, the swift currents race across thousands of miles. The Gulf Stream, the Kuroshio, the Agulhas. These are the sopranos of the ocean, bright and fast, carrying warm water from the tropics towards the poles. Below them, in the middle depths, flow the slower, more measured currents, the altos and tenors of our aquatic symphony. These waters move with purpose, but without haste, carrying nutrients and dissolved gases across ocean basins, connecting the surface world with the deep. And in the deepest places, where sunlight never reaches, flow the bass notes of the ocean, the deep, cold currents that creep along the ocean floor, carrying the memory of polar ice across the globe. These waters may take 1,000 years to complete their journey, moving from the Arctic to the Antarctic and back again, carrying with them the breath of ancient glaciers and the whispers of long-forgotten storms. To understand how currents form, we must think like the water itself. Water, you see, is never quite the same from place to place. In the tropics, it is warm and light, eager to float and spread. Near the poles, it is cold and heavy, content to sink and settle. Add salt to the equation. More salt makes water denser, less salt makes it lighter, and you have the basic ingredients for the ocean's great circulation. Picture the Mediterranean Sea, where the hot sun evaporates water faster than rivers can replace it. The remaining water becomes saltier, denser, and begins to sink. This dense water flows out through the Strait of Gibraltar, diving beneath the lighter Atlantic water like a river flowing upside down. It is one of the most beautiful examples of how the ocean sorts itself, layer by layer, according to the subtle differences in density. In the polar regions, the opposite happens. When seawater freezes, it leaves its salt behind, making the surrounding water denser. This cold, salty water sinks to the ocean floor and begins its long journey toward the equator, carrying with it the chill of the Arctic and Antarctic. It is a journey that may take centuries, but it connects every part of the ocean in an endless, patient circulation. Above the ocean's surface, the atmosphere plays its own part in the great dance of currents. The trade winds, born from the Earth's rotation and the uneven heating of land and sea, blow steadily across the tropical oceans, pushing the surface waters before them like a gentle, persistent hand. These wind-driven currents are the most visible and immediate of the ocean's movements. The Gulf Stream begins its life as the North Equatorial Current, pushed westward by the trade winds until it encounters the coast of North America and turns north, carrying tropical warmth toward Europe. The Kuroshio follows a similar path in the Pacific, bringing the warmth of the Philippines to the shores of Japan. But the winds do more than just push water around. They also create upwelling, the process by which deep, nutrient-rich water rises to the surface. Off the coasts of Peru, California, and West Africa, steady winds blow the surface water away from shore, allowing the cold, fertile water from below to rise and feed some of the ocean's most productive ecosystems. In the depths of the ocean, currents carry more than just water. They carry memory. The deep currents that flow along the ocean floor were born in the polar regions, where they absorb the cold of glaciers and the breath of icebergs. As they flow toward the equator, they carry this memory with them, a reminder of the ice ages and the changing climate of our planet. Scientists can read this memory by studying the chemistry of deep water, the oxygen content, the carbon isotopes, the trace minerals, all tell a story of where the water has been and what it has experienced. Some of the water in the deep Pacific may have last seen the surface 1,000 years ago in the North Atlantic, carrying with it the memory of medieval storms and the breath of Viking longships. This deep circulation is crucial to our planet's climate. It carries heat from the tropics to the poles and brings nutrients from the depths to the surface. Without it, the tropics would be unbearably hot, the poles would be frozen wastelands, and life as we know it could not exist. As we drift through this introduction to the ocean's invisible rivers, let us remember that every current is connected to every other. The Gulf Stream that warms Europe begins in the Caribbean and ends in the Arctic. The Antarctic Circumpolar Current, the mightiest of all ocean currents, connects the Atlantic, Pacific, and Indian Oceans in an endless loop around the bottom of the world. These connections mean that what happens in one part of the ocean affects every other part. A change in the trade winds over the Pacific can alter weather patterns around the globe. The melting of Arctic ice can slow the circulation of the North Atlantic, changing the climate of Europe. The ocean is not just a body of water. It is a single, interconnected system, as complex and beautiful as any living organism. Tonight, as we begin our journey through the secret lives of ocean currents, let us listen to the rhythm of the sea. It is a rhythm older than human civilization, older than the continents themselves. It is the heartbeat of our planet, the pulse that keeps our world alive and habitable. In the chapters that follow, we will trace the paths of individual currents, the Gulf Stream's warm embrace of the North Atlantic, the great conveyor belt that connects all the world's oceans, the Pacific's mighty gyres that dwarf entire continents. We will meet the creatures that ride these currents, the explorers who first mapped them, and the scientists who continue to unlock their secrets. But for now, let us simply rest in the knowledge that beneath every wave, behind every tide, flows an invisible river carrying the ocean's ancient wisdom from shore to shore. These currents are the arteries of our blue planet, and their stories are the stories of life itself. To truly appreciate the ocean's currents, we must understand the forces that create and sustain them. The primary drivers are simple in concept, but infinite in their complexity. Solar heating creates temperature differences, the Earth's rotation deflects moving water, and the gravitational pull of the moon and sun creates the tides that mix and stir the ocean's layers. But within this simple framework lies a world of extraordinary complexity. Currents can split and merge, speed up and slow down, dive deep or rise to the surface, all in response to the subtle interplay of forces that govern the ocean's behavior. A current that begins as a narrow stream may spread into a broad flow hundreds of miles wide. A surface current may suddenly dive to great depths, carrying surface water and all its dissolved gases into the ocean's interior. The mathematics of ocean currents involves equations that describe the motion of fluids on a rotating sphere, equations so complex that they can only be solved by the most powerful computers. Yet the basic principles are elegant in their simplicity. Water flows from high pressure to low pressure. Warm water rises, cold water sinks, and the Earth's rotation deflects all motion to the right in the northern hemisphere and to the left in the southern hemisphere. Just as the land experiences seasons, so too does the ocean. The monsoons of the Indian Ocean reverse the direction of currents twice a year, bringing life-giving rains to billions of people. The seasonal melting of Arctic ice sends pulses of fresh water into the North Atlantic, temporarily altering the strength of the Gulf Stream. The formation and melting of sea ice in the Antarctic creates seasonal variations in the deep currents that flow northward along the ocean floor. These seasonal changes are like the breathing of the ocean, a slow, deep rhythm that affects everything from the migration of whales to the spawning of fish to the formation of storms. The ocean remembers each season and carries that memory forward so that the effects of a particularly cold winter in the Arctic may not be felt in the tropics until years later. As our climate changes, so too do the ocean's currents. The warming of polar regions is reducing the temperature difference between the equator and the poles, potentially slowing the great conveyor belt of deep circulation. The melting of glaciers is adding fresh water to the ocean, changing its density structure and altering the paths of currents. Scientists study these changes with a sense of urgency, for the ocean's currents are intimately connected to our planet's climate. A significant change in circulation could alter weather patterns around the globe, affecting everything from the monsoons of Asia to the hurricanes of the Atlantic. The ocean's currents are not just beautiful, they are essential to the stability of our climate and the continuation of life as we know it. As we conclude this gentle introduction to the ocean's invisible rivers, let us remember that currents are more than just moving water. They are poetry in motion, the Earth's way of writing its story across the vast canvas of the sea. Each current carries within it the memory of its birth, the story of its journey, and the promise of its destination. The Gulf Stream carries the warmth of the Caribbean to the shores of Ireland. The Kuroshio brings the tropical heat of the Philippines to the temperate coasts of Japan. The Antarctic Circumpolar Current connects three oceans in an endless dance around the bottom of the world. These are not just movements of water. They are the threads that weave together the fabric of our planet's climate. Tonight, as you rest and let these thoughts settle like sediment in still water, remember that you are connected to every ocean current, every flowing river of the sea. The oxygen you breathe may have been dissolved in the waters of the Gulf Stream. The rain that falls on your garden may have evaporated from the warm waters of the Kuroshio. The very climate that sustains life on Earth is maintained by the endless, patient circulation of the ocean's invisible rivers. In the chapters that follow, we will dive deeper into these connections, exploring the individual currents that shape our world and the creatures that call them home. But for now, let the rhythm of the sea carry you gently toward rest, knowing that beneath the waves, the ocean's great rivers flow on, carrying their ancient wisdom from shore to shore, from season to season, from past to future, in an endless, beautiful dance of water and time. Drift with me now, gentle traveler, into the warm embrace of the ocean's most famous river, the Gulf Stream. This mighty current, born in the sun-drenched waters of the Caribbean, carries tropical warmth across thousands of miles of ocean, shaping the climate of 2 continents and the lives of countless creatures along its path. Tonight, we follow this liquid highway from its humble beginnings to its grand finale, listening to the stories it whispers as it flows. Close your eyes and imagine yourself floating in the crystal clear waters off the coast of Florida, where the Gulf Stream begins its epic journey. Here, the water is a brilliant turquoise, warm as a summer bath, carrying within it the memory of coral reefs, tropical storms, and the gentle trade winds that pushed it westward across the Atlantic. This is where our story truly begins, not with a single moment, but with the convergence of currents, the meeting of waters that have travelled from distant shores to create something magnificent. The Gulf Stream story begins long before it reaches Florida in the vast basin of the Caribbean Sea. Picture this tropical paradise, a sea enclosed by islands and continents, heated by the relentless sun, stirred by the trade winds that blow steadily from east to west. The water here is not just warm, it is energized, charged with heat that will eventually warm the shores of Ireland and Norway, thousands of miles away. The Caribbean current flows westward through this basin, carrying water that originated in the South Atlantic, passed through the equatorial regions, and absorbed the heat of the tropical sun. As this current encounters the Yucatan Peninsula, it is forced northward through the narrow Yucatan Channel, where it gains speed and focus, like a river entering a canyon. This is the moment of transformation, when the broad, leisurely Caribbean current becomes the focused, powerful Gulf Stream. The water accelerates as it passes through the strait, carrying with it not just heat, but nutrients, marine life, and the chemical signatures of its tropical origins. Scientists can trace these signatures thousands of miles downstream, reading the Gulf Stream's Caribbean birth certificate in the chemistry of its waters. As the newly focused current emerges from the Yucatan Channel, it hugs the western coast of Florida, becoming what oceanographers call the Florida Current. Here, confined between the Florida Keys and the Bahama Banks, the current reaches speeds that would make a river jealous, up to 4 miles per hour, fast enough to carry a message in a bottle from Miami to Cape Hatteras in just 2 weeks. Picture this underwater highway, a river within the sea, its boundaries as distinct as those of the Mississippi or the Amazon. The water is a deep, rich blue, warmer than the surrounding ocean, carrying with it the distinctive chemistry of its Caribbean origins. Dolphins ride its edges, sea turtles use it as a migration route, and countless species of fish depend on the nutrients and warmth it provides. The Florida Current is remarkably stable, flowing northward with the consistency of a great river. But unlike a terrestrial river, it has no banks of earth and stone, only the subtle differences in water density and temperature that create invisible boundaries as real as any shoreline. These boundaries shift and pulse with the rhythm of the tides, the pressure of the winds, and the deep, slow breathing of the ocean itself. At Cape Hatteras, North Carolina, the Gulf Stream encounters one of the most dramatic moments in its journey. Here, the continental shelf drops away into the deep Atlantic, and the current is suddenly free from the constraints of shallow water. Like a river emerging from a canyon into a broad valley, the Gulf Stream begins to meander, creating the graceful loops and eddies that make it one of the most beautiful features visible from space. These meanders are not random. They follow patterns as complex and beautiful as the spirals of a nautilus shell. The current swings eastward, then westward, then eastward again, creating warm core and cold core eddies that spin off like wheels from a cosmic chariot. Some of these eddies are hundreds of miles across and can persist for months or even years, carrying tropical water far into the North Atlantic or pulling cold northern water southward into warmer seas. From space, the Gulf Stream looks like a great blue river flowing through the darker waters of the Atlantic, its boundaries marked by the sharp contrast between warm and cold water. But this view, beautiful as it is, captures only a moment in time. The Gulf Stream is constantly changing, pulsing with life, responding to the winds above and the deep currents below. As the Gulf Stream flows northeastward across the Atlantic, it gradually loses its identity as a single, focused current and becomes part of the broader North Atlantic circulation. But its influence does not diminish. If anything, it grows stronger. The warm water it carries northward releases its heat to the atmosphere, warming the winds that blow across Europe and creating the mild climate that makes life possible at latitudes that would otherwise be frozen tundra. Consider this remarkable fact. London, at 51 degrees north latitude, enjoys a climate similar to that of cities 10 to 15 degrees farther south in North America. Paris, Rome, and Madrid all lie at latitudes that in North America would place them in Canada. Yet they bask in temperate climates that support agriculture, civilization, and millions of people. This is the gift of the Gulf Stream, a river of warmth flowing through the cold North Atlantic, sharing its tropical heat with distant shores. The mechanism is elegantly simple. As the warm Gulf Stream water flows northward, it evaporates, cooling the water and warming the air above it. This warm, moist air is then carried eastward by the prevailing westerly winds, bringing mild temperatures and abundant rainfall to Western Europe. Without the Gulf Stream, Europe would be a very different place, colder, drier, and far less hospitable to human civilization. But the Gulf Stream story does not end with the warming of Europe. As the current flows northward, it gradually cools, and as it cools, it becomes denser. In the waters around Greenland and Iceland, this now cold water begins to sink, diving deep into the Atlantic and beginning a new journey. This time along the ocean floor, carrying the memory of its surface travels into the deep. This sinking is one of the most important processes in the global ocean circulation. The cold, dense water that forms in the North Atlantic flows southward along the ocean floor, eventually reaching the Southern Ocean and mixing with waters from the Pacific and Indian Oceans. This deep water may not return to the surface for hundreds or even thousands of years, carrying with it the chemical signatures of its North Atlantic origins. This process, the sinking of surface water, and its replacement by deep water, is what drives the global thermohaline circulation, the great conveyor belt that connects all the world's oceans. The Gulf Stream is not just a regional current, it is part of a global system that regulates the Earth's climate and makes life as we know it possible. The Gulf Stream is more than just a river of warm water. It is a highway for marine life, a migration route that connects tropical and temperate ecosystems across thousands of miles of ocean. Sea turtles born on the beaches of Florida ride the current northward, feeding and growing in the rich waters of the North Atlantic before returning south to breed. Eels born in the Sargasso Sea use the Gulf Stream to reach the rivers of North America and Europe, where they will spend most of their adult lives. The current also creates unique ecosystems along its path. The Sargasso Sea, a vast area of the North Atlantic bounded by the Gulf Stream and other currents, is home to floating forests of sargassum seaweed that support a complex web of marine life. Flying fish, sea turtles, and countless species of small fish and invertebrates depend on these floating meadows for food and shelter. The boundaries of the Gulf Stream, where warm tropical water meets cold northern water, are particularly rich in marine life. These frontal zones, as oceanographers call them, are like underwater oases, where nutrients from the deep mix with warm surface water to create ideal conditions for plankton growth. The plankton, in turn, support fish, which support larger predators, creating a food web that extends from the smallest bacteria to the largest whales. For centuries, humans have known about the Gulf Stream and used it to their advantage. Native Americans, fishing off the coast of Florida, were aware of the current's power and used it to aid their journeys. European explorers, beginning with Ponce de Leon in the early 16th century, noted the strong current that could either aid or hinder their voyages. But it was Benjamin Franklin who first mapped the Gulf Stream scientifically, working with his cousin, Timothy Folger, a Nantucket whaling captain who had intimate knowledge of the current's path. Franklin's map, published in 1769, showed the Gulf Stream as a distinct river within the ocean, and his advice to male packet captains to avoid the current when sailing west and use it when sailing east could save weeks on a transatlantic voyage. The Gulf Stream continued to play a crucial role in maritime commerce well into the age of steam and beyond. During World War II, German U-boats used the current's warm water to hide their thermal signatures from Allied sonar. Today, oceanographers study the Gulf Stream with satellites, underwater gliders, and sophisticated computer models, seeking to understand its variability and predict its future behavior. Like all great rivers, the Gulf Stream has its seasons. In winter, when the temperature difference between the tropics and the poles is greatest, the current runs strong and steady. In summer, when the temperature gradient is reduced, the current may weaken and become more variable. These seasonal changes affect everything from the migration patterns of marine life to the storm tracks of hurricanes. The Gulf Stream also responds to longer-term climate cycles. During El Niño years, when the tropical Pacific is unusually warm, the Gulf Stream may shift its path or change its strength. During periods of strong Arctic ice formation, the increased production of cold, dense water in the North Atlantic can strengthen the deep return flow and intensify the entire circulation system. Scientists study these variations with the intensity of meteorologists tracking a storm. For changes in the Gulf Stream can have far-reaching consequences. A weakening of the current could alter weather patterns across the North Atlantic, affecting everything from the frequency of hurricanes to the severity of European winters. The Gulf Stream carries more than just heat. It carries memory. The chemical composition of its waters tells the story of its journey from the coral reefs of the Caribbean to the ice-covered seas of the North Atlantic. Scientists can read this chemical signature like a book, tracing the current's path and timing its journey with remarkable precision. Oxygen levels in the water reveal how long it has been since the water was last at the surface. Carbon isotopes tell of the photosynthesis that occurred in tropical waters. Trace metals carry the signatures of distant rivers and the dust of far-off deserts. Each chemical marker is a chapter in the Gulf Stream's story, a record of its travels written in the language of molecules and atoms. This chemical memory is crucial for understanding how the ocean works as a global system. By tracking the Gulf Stream's chemical signature, scientists can study how quickly water moves through the ocean, how nutrients are distributed, and how the ocean responds to changes in climate. The Gulf Stream becomes not just a current, but a laboratory for understanding the entire planet. As our climate changes, so too does the Gulf Stream. The warming of the Arctic is reducing the temperature difference that drives the current, potentially weakening its flow. The melting of Greenland's ice sheet is adding fresh water to the North Atlantic, making the water less dense and reducing the sinking that drives the deep return flow. These changes are not just academic concerns. They have real implications for the millions of people who depend on the Gulf Stream's warming influence. A significant weakening of the current could alter weather patterns across the North Atlantic, bringing colder winters to Europe and changing precipitation patterns across the region. Scientists monitor these changes with a network of instruments that spans the entire Atlantic Ocean. Moored buoys measure the current's temperature and speed. Satellite altimeters track the height of the sea surface, which reveals the current's strength and path. Computer models simulate the current's behavior under different climate scenarios, helping us understand what the future might hold. As we conclude our journey along the Gulf Stream's path, let us remember that this current is more than just moving water. It is one of the great rivers of our planet, as mighty and important as any that flows across the land. It connects the tropics to the poles, the Caribbean to Europe, the surface to the depths. It carries heat, nutrients, and life across thousands of miles of ocean, shaping the climate of continents and the evolution of species. The Gulf Stream reminds us that the ocean is not a barrier, but a highway, not a void, but a living system that connects every part of our planet. In its warm embrace, we see the unity of Earth's climate system, the delicate balance that makes our world habitable, and the beauty of natural processes that operate on scales both vast and intimate. Tonight, as you rest and let these thoughts settle like the gentle rocking of a ship at anchor, remember that the Gulf Stream flows on, carrying its cargo of warmth and life from the Caribbean to the Arctic, from past to future, in an endless journey that began millions of years ago and will continue long after we are gone. It is one of the great constants of our changing world, a river of hope flowing through the vast blue heart of our planet. Welcome, gentle dreamer, to the grandest journey of all, the story of the ocean's great conveyor belt, a circulation system so vast and powerful that it connects every drop of water in every sea, carrying the breath of the Arctic to the depths of the Pacific and the warmth of the tropics to the frozen shores of Antarctica. This is the thermohaline circulation, named for the twin forces that drive it: temperature, thermo, and salt, haline. Tonight, we embark on a voyage that will take us around the entire globe, following waters that may not return to their starting point for 1,000 years or more. Close your eyes and imagine the ocean not as separate seas and basins, but as a single, interconnected system, a vast circulatory network like the bloodstream of our planet. Just as blood carries oxygen and nutrients to every cell in your body, the great conveyor belt carries heat, nutrients, and dissolved gases to every corner of the ocean, maintaining the delicate balance that makes life on Earth possible. The great conveyor belt begins in the most unlikely of places, the cold, stormy waters of the North Atlantic, where winter winds howl across the surface and icebergs drift like ghostly cathedrals through the grey twilight. Here, in the waters between Greenland, Iceland, and Norway, something remarkable happens. The warm surface water that travelled thousands of miles from the tropics finally surrenders its heat to the atmosphere and begins its long journey into the deep. Picture this transformation. Water that was once turquoise and warm, heated by the Caribbean sun and carried northward by the Gulf Stream, now grows cold and dense under the Arctic sky. As it cools, it becomes heavier than the water around it, and like a stone dropped into a pond, it begins to sink. But this is no ordinary sinking. This is the birth of a deep current that will flow along the ocean floor for thousands of miles, carrying with it the memory of its surface journey and the promise of renewal. This process, called deep water formation, is one of the most important phenomena in the ocean. The sinking water doesn't just disappear, it forms the North Atlantic deep water, a distinct water mass that flows southward along the ocean floor, carrying with it high levels of oxygen and nutrients that will eventually nourish marine life in distant seas. Follow this newly formed deep water as it begins its epic journey southward, moving slowly but steadily along the ocean floor. It carries with it the chemical signature of its North Atlantic origins, high oxygen content from its recent contact with the atmosphere, and the distinctive isotopic ratios that mark it as clearly as a passport stamp. This deep current flows beneath the Gulf Stream, beneath the warm surface waters of the tropical Atlantic, beneath the storms and calms of the surface world. It is a river of cold, dense water flowing through the darkness, guided by the subtle topography of the ocean floor, the underwater mountains and valleys that channel its flow like the banks of a terrestrial river. As it flows southward, this deep water gradually warms and loses some of its distinctive characteristics, mixing slowly with the waters around it. But its journey is far from over. At the southern tip of Africa, where the Atlantic meets the Southern Ocean, the North Atlantic deep water encounters the mightiest current on Earth, the Antarctic Circumpolar Current. The Southern Ocean, surrounding Antarctica like a vast moat, is home to the most powerful current system on our planet. The Antarctic Circumpolar Current flows endlessly around the continent, driven by the fierce westerly winds that blow across these latitudes. This current is unique. It is the only current that flows completely around the globe, connecting the Atlantic, Pacific, and Indian Oceans in an endless loop. Here, in the cold waters around Antarctica, the Great Conveyor Belt encounters its second engine. Just as the North Atlantic produces deep water through cooling and sinking, the Southern Ocean creates its own deep water masses through the formation and melting of sea ice. When seawater freezes, it leaves its salt behind, making the remaining water denser and causing it to sink. This Antarctic bottom water is even denser than the North Atlantic deep water, and it flows along the very bottom of the ocean beneath all other water masses. The Antarctic Circumpolar Current acts like a great mixing bowl, stirring together waters from all three oceans and distributing them around the globe. The North Atlantic deep water that began its journey in the cold seas near Greenland now mixes with waters from the Pacific and Indian Oceans, becoming part of a truly global circulation system. From the Southern Ocean, our water molecules, now part of the global mix, begin their journey northward into the Pacific. This is the largest and deepest of the world's oceans, and the journey across it is the longest leg of the Great Conveyor Belt's voyage. The deep water flows slowly northward, taking centuries to cross the vast Pacific basin. In the deep Pacific, far from the sunlight and storms of the surface, the water gradually warms and accumulates nutrients from the slow rain of organic matter falling from above. This is the ocean's great recycling system. Nutrients that were once part of living organisms in the surface, waters slowly dissolve and accumulate in the deep, waiting to be returned to the sunlit zone where life can use them again. The Pacific leg of the journey is the longest and most patient part of the Great Conveyor Belt. Water that sank in the North Atlantic may spend 500 to 1,000 years crossing the Pacific, slowly warming and changing as it flows through the darkness. This is deep time made manifest, a journey so long that the water remembers climates that existed before the rise of human civilization. Eventually, our ancient water reaches the northern Pacific, where it begins its return to the surface. This upwelling happens gradually, driven by the winds and currents of the surface ocean. In some places like the coasts of California and Peru, strong winds blow surface water away from shore, allowing the deep water to rise and replace it. In other areas, the mixing is more gradual, a slow stirring that brings deep water toward the surface over broad areas of the ocean. When this ancient water finally reaches the surface, it carries with it the accumulated nutrients of its long journey. These nutrients, nitrogen, phosphorus, silica, and trace metals, are like fertilizer for the ocean's plant life. The phytoplankton that form the base of the marine food web depend on these nutrients, and their abundance in upwelling areas creates some of the most productive ecosystems on Earth. The Great Conveyor Belt has another branch that flows through the Indian Ocean, creating a complex three-dimensional circulation that connects all the world's seas. Water from the Southern Ocean flows northward into the Indian Ocean, where it gradually warms and rises toward the surface. Some of this water eventually flows westward around the southern tip of Africa, rejoining the Atlantic circulation and completing another loop of the global system. The Indian Ocean circulation is influenced by the monsoons, the seasonal winds that bring life-giving rains to billions of people in Asia. During the summer monsoon, winds blow from the southwest, driving surface currents and upwelling patterns that affect the entire ocean. During the winter monsoon, the winds reverse, creating a different pattern of circulation. This seasonal reversal makes the Indian Ocean unique among the world's oceans, a place where the Great Conveyor Belt pulses with the rhythm of the monsoons. To truly appreciate the Great Conveyor Belt, we must think in terms of deep time, the vast scales on which the ocean operates. A water molecule that sinks in the North Atlantic today may not return to the surface for 500 to 1,500 years. During that time, it will travel tens of thousands of miles, crossing entire ocean basins and carrying with it the chemical memory of its journey. This means that the deep ocean contains water from many different eras. Some of the water in the deep Pacific lasts saw the surface during the medieval warm period, when Vikings were exploring the North Atlantic and the Maya civilization was flourishing in Central America. Other water may have sunk during the Little Ice Age, carrying with it the memory of a colder world. Scientists can read this history in the chemistry of deep water. The oxygen isotopes tell of ancient temperatures. The carbon isotopes reveal the state of past ecosystems. And the radioactive tracers show how long the water has been isolated from the atmosphere. The deep ocean is a vast library of climate history, written in the language of chemistry and preserved in the slow circulation of the Great Conveyor Belt. The Great Conveyor Belt is not just a curiosity of oceanography, it is one of the most important regulators of Earth's climate. By carrying heat from the tropics toward the poles and bringing cold water toward the equator, it helps to moderate the temperature differences that would otherwise make our planet uninhabitable. The conveyor belt also plays a crucial role in the carbon cycle. When water sinks in the North Atlantic, it carries with it dissolved carbon dioxide from the atmosphere. This carbon is then stored in the deep ocean for centuries, helping to regulate the amount of CO2 in the atmosphere. When the water eventually returns to the surface, it releases this carbon back to the atmosphere, completing the cycle. Changes in the strength of the Great Conveyor Belt can have profound effects on global climate. During the last ice age, the conveyor belt was much weaker than it is today, and some scientists believe that sudden changes in its strength may have triggered rapid climate changes in the past. Understanding how the conveyor belt works is crucial for predicting how our climate might change in the future. Despite its immense size and power, the Great Conveyor Belt is surprisingly vulnerable to change. The sinking of water in the North Atlantic depends on the water being dense enough to sink, which requires it to be both cold and salty. Global warming is making the surface water warmer, while the melting of Greenland's ice sheet is making it fresher. Both of these changes make the water less dense and could potentially slow or even shut down the formation of North Atlantic deep water. Such a shutdown would have catastrophic consequences for global climate. Europe would become much colder, as it would lose the warming influence of the Gulf Stream. The tropical Atlantic might become warmer, potentially leading to more intense hurricanes. The patterns of rainfall around the world could shift, affecting agriculture and water supplies for billions of people. Scientists monitor the Great Conveyor Belt with the same intensity that doctors monitor a patient's vital signs. Arrays of instruments measure the temperature, salinity, and flow of water at key points in the circulation. Satellites track the height of the sea surface, which reveals the strength of the currents below. Computer models simulate the circulation under different climate scenarios, helping us understand what the future might hold. Beyond its role in climate regulation, the Great Conveyor Belt serves as a vast nutrient distribution system for the ocean. The deep water that forms in the North Atlantic is rich in oxygen, but poor in nutrients. As it flows through the deep ocean, it gradually loses oxygen and gains nutrients from the decomposition of organic matter falling from above. By the time this water reaches the Pacific and begins to upwell, it has become a nutrient-rich soup that feeds some of the most productive ecosystems on Earth. The upwelling zones off Peru, California, and West Africa are among the richest fishing grounds, supporting vast populations of fish, seabirds, marine mammals, and entire coastal economies. This nutrient transport is essential for maintaining ocean productivity. Without the Great Conveyor Belt to redistribute nutrients from the deep to the surface, the ocean would become stratified, trapping nutrients in deep water and leaving surface waters barren. The conveyor belt keeps the ocean alive by recycling nutrients from the depths to sunlit surface waters, where life thrives. The fate of the Great Conveyor Belt is a crucial question in climate science. Will it continue as it has for millennia, or will human activities weaken or halt it? Current models suggest significant weakening over the next century, but a complete shutdown is unlikely, though uncertainty remains. The ocean is a complex system, and small changes can have large, unexpected consequences. The conveyor belt has changed dramatically in the past, sometimes shutting down and restarting. These shifts offer clues about future behavior and remind us that the system is not as stable as it appears. As we conclude our journey around the Great Conveyor Belt, marvel at its scale and complexity. It connects every ocean and sea, every drop of water, in a single, vast circulation, operating for millions of years. It is both ancient and eternal, carrying the memory of past climates and shaping the climate of the future. The Great Conveyor Belt reminds us that the ocean is a single, interconnected system. What happens in the Arctic affects the tropics, the Atlantic affects the Pacific, and the surface affects the deep. We are all connected by the slow, patient circulation of the sea. Tonight, as you rest, remember you are part of this system. The oxygen you breathe may have dissolved in the North Atlantic. The rain on your garden may have evaporated from the Pacific. The stability of our climate depends on the continued operation of this vast, invisible river that flows through the depths. In the chapters that follow, we'll explore the specific currents of the Pacific, the creatures that ride these flows, and how ocean circulation connects all life. For now, let the rhythm of the Great Conveyor Belt carry you gently toward rest, knowing that beneath the waves, the ocean's greatest river flows on, carrying the breath of the planet from pole to pole, from surface to depth, from past to future. Welcome, gentle traveler, to the vast expanse of the Pacific Ocean, the largest and most ancient of Earth's seas, stretching from the Arctic to Antarctica, from volcanic islands to golden beaches. Here, some of the mightiest and most beautiful currents on Earth flow. Tonight, we drift with these liquid highways, following their ancient paths as they carry warmth, life, and memory across thousands of miles. Imagine the Pacific as a living tapestry of flowing rivers, each current a thread connecting Asia to the Americas, tropics to poles, surface to depths. These currents have shaped the climate of continents, guided migrations of whales and sea turtles, and carried explorers' dreams across the world's greatest ocean. Begin in the warm waters off the Philippines, where the North Equatorial Current gathers sun-heated waters and carries them westward. Here begins the Kuroshio, or Black Current, named for the deep indigo colour of its warm, nutrient-poor waters. The North Equatorial Current, flowing westward, encounters the Philippines and Taiwan, is forced northward and becomes the swift, powerful Kuroshio, the Gulf Stream of the Pacific. The Kuroshio hugs the eastern shores of Taiwan and Japan, carrying tropical warmth northward at speeds up to 4 knots. Like the Gulf Stream, it creates a distinct boundary between warm and cold water, visible from space as a ribbon of deep blue. As the Kuroshio flows northward, it brings more than warm water. It brings life. The current carries larvae of tropical fish, seeds of marine plants, and nutrients that feed Japan's coastal ecosystems. The warm water moderates Japan's climate, enabling rice cultivation at latitudes where only hardy grains might survive. At the latitude of Tokyo, the Kuroshio encounters the open ocean and begins to meander, creating the Kuroshio Extension, a river of warm water flowing through the cold North Pacific, one of the most dynamic ocean regions. On the eastern Pacific, the California Current flows southward along the coasts of California, Oregon, and Washington. It is cool, nutrient-rich, and green with life. The California Current begins in the subarctic North Pacific, where westerly winds drive surface water eastward. When this cold water reaches North America, it is deflected southward, creating a broad, slow-moving river of cool water. The California Current's magic lies in upwelling. Northwesterly winds push surface water away from shore, allowing cold, nutrient-rich water to rise. This process transforms the California Current into one of the most productive marine ecosystems on Earth, feeding vast blooms of phytoplankton that support huge populations of fish, seabirds, and marine mammals. At the heart of the Pacific, straddling the equator, flow the equatorial currents, a complex system of eastward and westward flows that connect the Americas to Asia and play a crucial role in global climate. The north and south equatorial currents flow westward, carrying warm water toward Asia. Between them, the equatorial countercurrent flows eastward, creating a complex pattern that influences weather worldwide. Beneath the surface, the equatorial undercurrent, Cromwell Current, runs eastward, carrying cool, nutrient-rich water toward the Americas and supporting unique ecosystems like the Galapagos. All these currents, the Kuroshio, California Current, North Equatorial, and North Pacific, are linked in the North Pacific Gyre, a vast circular flow that spans the entire North Pacific and takes decades to complete. This gyre is a moving habitat supporting marine life across thousands of miles. Sea turtles born in Japan ride the gyre, feeding and growing in the California Current before returning to breed. Albatrosses and seabirds use the gyre's currents for long-distance flights. The South Pacific has its own gyre, with the East Australian Current bringing tropical water south and the Peru Current supporting vast fisheries through upwelling. The South Equatorial Current connects these, influencing the climate of the entire South Pacific. The Pacific's currents pulse and change with global weather cycles. The most famous is El Niño, a periodic warming of the eastern tropical Pacific that alters current strength and direction. During El Niño, trade winds weaken, allowing warm water to flow eastward, triggering droughts in Australia, floods in California, and global weather changes. La Niña, the opposite phase, brings stronger trade winds and enhanced upwelling, supporting massive populations of fish and seabirds, but also altering global storm patterns. Beneath the surface, deep water masses are part of the global thermohaline circulation. The Pacific is the final destination for much of the deep water that begins in the North Atlantic. This ancient water, isolated for centuries, carries accumulated nutrients, making the deep Pacific one of the most nutrient-rich water masses. When it upwells, it fuels some of the most productive ecosystems on Earth. The Pacific's currents are highways for marine life, enabling migrations that span entire ocean basins. Whales follow these currents on annual journeys from Arctic feeding grounds to tropical breeding areas. Sea turtles ride the gyres for decades, navigating by magnetic fields, chemical cues, and current patterns. The currents also transport larvae of countless species, connecting populations and maintaining genetic diversity. Polynesian navigators use their knowledge of currents, winds, and waves to explore and settle islands across the Pacific. Modern shipping still relies on these currents to reduce fuel consumption and travel time. Pacific currents regulate Earth's climate, carrying heat from the tropics to the poles and bringing polar water toward the equator. Upwelling systems along the eastern Pacific coasts support rich marine ecosystems and influence weather patterns across continents. Changes in currents can have far-reaching consequences as climate change alters upwelling systems and the distribution of marine life. As we conclude our journey, marvel at the scale and complexity of the Pacific. Its currents connect shores separated by thousands of miles, from the warm Kuroshio to the nutrient-rich California Current, from great gyres to deep currents carrying ancient water. The Pacific is a testament to the power and beauty of our ocean planet. These currents remind us that the ocean is a living system, not a barrier, but a highway, carrying warmth, life, and the breath of our planet in an endless dance of current and tide. Tonight, as you rest, remember that the Pacific's currents flow on, carrying their cargo of warmth and life from Asia to the Americas, from tropics to poles, in patterns as ancient as the ocean itself. They are the arteries of our blue planet, and their stories are the stories of life, climate, and the endless connections that bind our world together.